Okay, and in the last part of this course, we are going to learn how to modify and optimize existing RFEM models. So we've been seeing throughout this course that, for instance, with each RFEM component, we have this modify panel here, but we haven't used it so far. And now it's the moment in which we are going to see how to use this modify option and, more importantly, when to use it. So we have a trust structure here, and in RFEM, basically an already defined RFEM model, and this is the one that we are going to modify. So we have our members here, this trust structure, our loads and load cases, load combinations, and we also have load combinations of the RFEM module still EC3 to design still members according to the Eurocode 3, but let's leave that for the last part of this segment. Because now we are going to modify our nodes in case that we wanted to change the geometry of any particular structure. So of course, the first thing we need to do is to get our RFEM objects into Grasshopper. And for that, as you know, we have to use the getData component, this one. So now let's get a button to get the nodes and a toggle to get the nodes. But in this case, what we are going to do is to modify the geometry, the position, just of the nodes of the lower chord, because basically we want to change the height of the truss, so we don't need them to move the upper chords, the nodes of the upper chord at all. So what we need to do basically is to filter the nodes so that we get just the ones in this lower chord of our truss structure. So as you know, we need to get the filter here, the nodes option, that's right, and now we have to go to advanced option and we need to specify the C coordinate. So if we take a look into RFEM, we can realize that these nodes are in C coordinate -3. So we need to get those ones, and in order to specify the coordinate, remember, we have to specify not a number but a domain. So let's construct a domain. There we go, construct domain. And we have to say -3, because we want the points just at that location. And of course, the reason for specifying a domain is to specify a range of objects in case that we wanted several points in several locations and so on and so forth. Okay, but let's move these things a bit to the right part. And let's get our nodes. So here we have our nodes. Let's check very quickly if this is working. And those are my nodes. Perfect. So I'm just getting the nodes in the lower chord. And those are the objects that I want to modify. So in order to do that, it is actually very easy. So what we need to do is to get our RFEM objects, and we have to pass them into this input parameter here, RFEM node. But in case that we were modifying members, we should have to pass the members inside of this RFEM member parameter, and so on and so forth. That's very intuitive. And now we have to specify modify to true, because we want to modify those objects. Otherwise, what we would be doing is creating new objects in RFEM with the same properties as the existing ones. And now what we need to do is to specify the coordinates of the new nodes. So in case that we, if we wanted to move those points like 1 meter, like downwards, we would need to get the move component here, and now we would just need to specify the C coordinates, and let's say if we were moving them like 1 meter downwards, that would be the way. And now of course we need just another set data component, so we can pass the modify nodes, and here let's do this with a button for now. So if we click here in the button, now remember, we should be moving our nodes of the lower chord like 1 meter downwards. So let's try it out. And if we click on the button, we can see that, yeah, that's right, we have moved the nodes 1 meter downwards, and as a result, the whole geometry of the structure is being modified. So this is very interesting. But what we are going to do is not to define the new coordinates with a move component, but with the absolute coordinates. So for that, we are going to specify a slider. There we go. And let's start with minus, for instance, -5. So that should be the coordinates of our new point. So just we are going to get the original coordinates, and we are going to construct nodes or points in the same location, but with this new seed coordinate, in this case of -5. And let's delete these guys here. We don't need them anymore. Let's put this thing here, and if we click on run once again, now we should see that the lower chord is located exactly in the coordinate -5. Yeah, that's right, -5. Okay, so this is actually very powerful because now we are just moving all the points to the same location, let's say, to the same height, but we could also give like this truss structure like a curve shape, or we could do whatever we wanted with it. And it is even more interesting because we are making a RFEM model parametric, but we didn't start off with a parametric definition in Grasshopper, but we started off with an existing RFEM model. So I think that this approach is actually very interesting, and we cannot just modify node coordinate, but we can modify RFEM objects in many different ways. For instance, we can change the cross sections of the different members, we can change the thickness of a particular surface element, so we can do anything we want with existing RFEM elements. And what we are going to do now is to use this resource not just to modify the structure, but to optimize it. So we have basically two options to optimize a structure. The most common one would be to get the this guy here, the calculate model component. So a couple of minutes ago we were using the get results component, and with this component we are getting results of already calculated load cases and load combinations into Grasshopper. But with this other component, calculate model, we are going to actually calculate load cases and load combinations in RFEM in case that we wanted to get, I don't know, displacement in this case, or something else, as we are going to see. So how does this work? What we need to do, that's right, is to specify a button or even a toggle to run. So a toggle would be interesting when we are going to do this process again and again and again, as we are going to see in just 1 second. And now we have to specify the load case as we did for the get results component. So in this case, we are going to get the results of the load combination number 1, which is like ultimate limit state. So let's specify load combo number 1, and remember the keywords for this load case and combination. So you can say either load case, load combo, or result combo, depending on the result that you want to import. And now that should be it, because we have just one open model, so we don't need to do anything with this parameter here. And let's leave the trigger empty for now. So if we click on run, you can see that RFEM is calculating, and the calculation should be over, which means that we are getting the displacement here. Perfect, that's right. And now, what we are going to do is to couple this calculation option with the modification of our node. So let's set this thing to off, and if we trigger, means that we have to specify when this parameter changes, we are going to run this component, which means we are going to run the calculation into RFEM. So when the nodes are modified, we are going to start the calculation, and we should get this to true, because we are going to do this again and again and again for the optimization process, and this should be true as well. But the results are already here, so we don't need to do anything. But now it gets interesting, because if I modify this C coordinate, let's see, -3, now I modify the coordinates, but now the calculation is being triggered with this component. So I'm calculating the model when I'm modifying it, which it is very interesting. And as output of this component, I get the displacement here, but this is like a vector, so let's deconstruct it to get just the C coordinate. And we can see, for instance, this could be the result. So I really like it, I'm sorry. So this is in this case 0.2, this would be like meters, so 30 centimeters, okay, not bad. And we can see, for instance, when we do this, like instead of -3, -6, so we can see how the deformation is much lower now, just 10 centimeters. And yeah, of course, because the upper chord is located in the coordinate 0, C0, so we are specifying basically the truss height with this parameter. But it's very nice. But of course, we could use this input parameter to trigger an optimization process. And how do we do optimizations in Grasshopper? So there are many different plugins for that, but probably the most common one is Galapagos. So if we get Galapagos into our, let's get the panel back into Grasshopper. So if we get Galapagos here, we can specify as fitness the deformation that we wanted to minimize, and as genes we are going to specify the coordinate of our structure, and we just need hopefully, we just need to make double click into Galapagos and set fitness. We want to minimize the fitness which is the deformations, and solvers, let's basically start our solver. So let's put these guys here and let's go for it. So start solver, and we can see how we are starting our calculation, and we are modifying the height of our truss structure. We are getting the deformations in real time, and we are using these results to optimize our structure. In this case, it doesn't make much sense, because of course the parameter who is going to result in the lowest deformation should be the highest one, in this case 6 meters. But this is just an example how to run an optimization. So let me try to stop the solver. There we go. So okay, and this was just an example, sorry. But for instance, in this case, we're using the deformation as optimization parameter. But if you want it, we could, I'm not going to do it, but we could combine this component, this run calculation component, with the get results component, because here we are getting the load case that we are optimizing. So we could get this guy here, and we could even use that as a trigger. So that could be another option of getting different calculation results that we could optimize. But we are not going to do that, but we are going to use the last component of our toolbox at the current moment, which is the optimize cross sections one. And it works very similarly to this one, but it is focused on the RFEM module still Eurocode 3. So what we need to do is basically exactly the same. We need run parameter and the load combination. So these are the load combination which is already defined here, and since we can just have like load combinations, we don't need to do anything else. So that should be it, load combinations. Probably we should need to do something like that. And okay, load combination, and trigger the nodes as we were doing before, and as output parameter we are getting the steel mass, which is the value that we are going to optimize. So let's get the steel mass here, and let's try the same process with Galapagos, but now it should make more sense. Just give me 1 second, because in this case the fitness is the steel mass of our structure and the same optimization parameter, the same gene that is the coordinate or the height of our truss structure. So now let's go for it. Now it is running perfect, and we can start the optimization process. So minimize mass of steel, and by the way, if you take a look into Grasshopper, you can realize that the cross sections changed, because now we're optimizing them with the optimized cross section component. That's basically what this component does. It optimizes cross sections. So now in each iteration, we are going to try a new structural height, and we are going to optimize the cross sections for those height. The idea is to find the optimal height of the structure. So of course, if the truss could be like a very slender one, we would get very relatively high member forces, so very big cross sections, and we would get a very big amount of steel. On the other hand, if we choose a very high value for the height of our truss structure, the members could be very long, and although the member forces could be relatively low, the steel mass would also be very high. So we need to find the optimal value for that, and in order to do this properly, of course, we need to optimize the cross sections in each iteration. So that's what we are doing. Let's try it out. So start solver, and we can see how we are trying different heights here, 4.979, that's right. And if you take a closer look into RFEM, you can see how we're optimizing the cross section in each iteration, which I think it is very interesting. And I think this is a very, interesting and holistic approach. And this is basically all the options that you have within the toolbox to modify and optimize Grasshopper model. So let's stop the solver at this point. Let's see what results we are getting. Okay, so we are getting a truss. In this case, it is 3.3. And I think the steel mass is lower than the value that we started off with. So that could be a satisfactory result for our optimization. And that would be everything from our course regarding the parametric finite element toolbox. Thank you very much.